Standard language models force the engine that performs logical reasoning to also store every fact about the world within the exact same system. This approach relies on parametric memory, where world knowledge is trapped directly inside the neural weights of the network. This creates a significant engineering hurdle. Because the facts are baked into the parameters, updating the model's knowledge requires modifying the weights themselves, a process involving expensive retraining or fine-tuning. Relying solely on these weights introduces further complications. The system offers no direct provenance for its answers, and when the weights contain stale data, the model often generates plausible-sounding but false information. While the model's reasoning capabilities remain, its database of facts begins to diverge from reality the moment the training process concludes. In 2020, researchers at Facebook AI, UCL, and NYU published a paper proposing a structural solution. Their primary objective was to fundamentally decouple the active reasoning process from the heavy, rigid burden of long-term memorization. The solution they introduced is retrieval-augmented generation, or RAG. It works by adding a second, externalized memory system to the architecture. The second layer is non-parametric memory, a searchable, dense index originally containing 21 million chunks of Wikipedia. Instead of relying purely on internal weights, the generator model consults this index at inference time to pull the exact information it needs for a specific prompt. The performance implications are immediate. By moving knowledge into the index, the researchers demonstrated that a 626 million parameter RAG model could outperform a massive 11 billion parameter T5 model on open domain question answering. To understand how a model a fraction of the size achieves that accuracy, we have to look at the exact data flow of the architecture, from the retriever to the generator. This decoupling allows lean models to operate with the knowledge capacity of much larger systems by offloading the storage of facts to the external index. The system queries the non-parametric memory using a mechanism called the dense passage retriever, or DPR. The DPR bi-encoder passes a query through one BERT encoder and documents through another. Similarity is calculated via the inner product of their vectors. A maximum inner product search then isolates the top K matching documents. The document encoder within the architecture is intentionally frozen. Because the document encoder is frozen, all 21 million document vectors are pre-computed. The index never needs to be rebuilt during the training loop or during generation. This pre-computation makes non-parametric memory viable at inference time. It removes the latency bottleneck that would occur if the model had to re-encode the entire library for every query. A common misconception is that RAG simply retrieves a document and pastes it into the prompt as context. RAG treats the retrieved document as a probabilistic latent variable. The system's BART generator does not commit to a single best document. Instead, it marginalizes over the top K retrieved results, weighing each one based on its retrieval probability. This marginalization happens two ways. RAG sequence assumes a single retrieved document is the latent cause for the entire sequence. The model calculates probability for the whole answer based on one document at a time, then sums those probabilities. The second variant is RAG token. RAG token marginalizes at the individual token level. By summing over documents for each specific token, the model can mix facts from different sources within a single answer. Marginalizing over latent documents provides a mathematical framework for the model to synthesize information without being tethered to a single source. During training, the system receives no explicit instruction on which specific documents are the correct ones to retrieve. Instead, the architecture is trained end-to-end by minimizing the marginal negative log likelihood. The gradient flows backward from the final answer, through the generator, and into the query encoder. To maintain numerical stability while training this probabilistic structure, the marginalization is performed in log-sum exp space. The retriever learns which documents are useful from the downstream generation loss. This creates a self-optimizing engine that requires no humans to label search results. The 626 million parameter RAG model outperforms the 11 billion parameter T5 model, proving the index provides the necessary knowledge. On a factuality metric, standard BART scores 7.1%, while the RAG version achieves 42.7%. Perhaps the most practical proof of this externalization is the hot swappable index.
By swapping a 2016 Wikipedia index for a 2018 version, the model's knowledge of world events is instantly updated. This update occurs without any retraining of the model's weights. The hot swappable index demonstrates that knowledge has been successfully moved out of the weights, allowing for modular updates to the model's worldview. The system does have defined boundaries, particularly when evaluated against the Fever fact verification dataset. RAG's unsupervised retrieval trails behind models that use explicit retrieval supervision by 4.3% on the Fever task. The architecture is also subject to a failure mode known as retrieval collapse. On tasks where the downstream gradient is weak, like open-ended story generation, the retriever may stop exploring and return the same irrelevant documents repeatedly. Additionally, RAG sequence decoding is computationally intensive due to the multiple forward passes required to sum over retrieved documents.
Despite these limits, the architecture relies on three core pillars: a non-parametric memory, marginalization over latent documents, and offloading facts from weights. By establishing this framework, the RAG paper created the template for the search-augmented assistants and knowledge agents in use today.